Welcome back to the Deep Dive. Today, we're not just looking at a revolutionary aircraft concept. We are forensically examining the engineering specification, the blueprint, really, that determines whether that aircraft can actually fly passengers safely and legally.
That's right.
We're diving into the colossal challenge of integrating and verifying the P-13 series parallel hybrid propulsion system for, the next generation of urban air mobility vehicles.
It's the ultimate systems engineering test, and quite frankly, it's the prerequisite for making UAM commercially viable beyond just the city limits.
Right.
The reality that drove this whole design choice is, well, it's straightforward. Range anxiety.
Range anxiety. We hear that with electric cars all the time.
Exactly the same principle. If you look at pure battery electric eVTOLs right now, we are just completely constrained by the current state of lithium battery technology.
And what's the number on that?
You're typically looking at an energy density in the 160 to 250 watt-hour per kilogram range.
And what does that mean practically for the passenger?
It means short, constrained routes. I mean, if you need to ferry people between major metropolitan hubs, say London to Paris or, New York to Boston, you are looking at intercity distances of 200 to 400 kilometers.
Which current batteries just can't do.
They can't do it reliably. Not with the required safety margins and the payload you need. They just don't carry enough usable energy per unit of weight.
Yeah.
It's a fundamental physics problem for now.
So the solution is hybridization. And that's where this P-13 architecture comes in. It's the strategic bridge, then, between today's battery limits and tomorrow's longer range requirements.
That's a perfect way to put it.
But for our listener who might be familiar with, say, a hybrid car, can you quickly break down the P-13? What are its key mechanical components?
Absolutely. Think of the P-13 as a masterclass in power flow management. The core concept strategically combines the high energy density of aviation fuel through an internal combustion engine, or ICE, with the responsive high-torque power delivery of electric motors. So we have three main players in the powertrain. First, the ICE itself, which provides that steady, long-term cruise power. Second, we have two electric machines. P3 is the main propulsion motor, which directly drives the rotors or the propellers.
I'm a surge.
Third, we have P1. P1 is an integrated starter generator, an ISG. It's primarily used for starting the ICE, managing the battery's state of charge, the SOC, and, critically, for performing active damping. We'll get into that later.
Okay, so ICE, P3 motor, P1 generator, and the piece of hardware that ties this whole complicated knot together.
That would be K0, the decoupling clutch.
T0.
Yep. K0 is the strategic gateway. When the aircraft is taking off or landing vertically, K0 is open, and we rely purely on electric power battery to P3.
Which gives you that precise control.
Precise, rapid thrust control. Then, when we transition to high-speed cruise, K0 engages, linking the ICE to the propulsion system. That lets us leverage the fuel energy density for range, while P1 manages the efficiency.
It sounds brilliant, as we've noted before, but that deep coupling of an ICE, a battery, a clutch, multiple motors, it just instantly creates a geometric nightmare of complexity.
It does.
It's not just electric failure anymore. It's electric failure, plus a mechanical failure, plus a thermal failure, plus a control system failure, all interacting at the same time.
Precisely. And that complexity is why the traditional aerospace method, the build then test paradigm, is utterly obsolete here. It just doesn't work.
You can't risk it.
We cannot risk finding catastrophic interacting failure modes 100 hours into flight testing. When you are developing a vehicle with this many tightly coupled mechatronic systems, you have to prove safety before you cut metal.
And that takes us directly to the mandate at the heart of this deep dive.
The technical specification is unambiguous. To achieve certification, specifically the enhanced category under ISO SC VTOL, the probability of a catastrophic failure must be proven to be below 10 to the minus 9 per flight hour.
1 in a billion.
One chance in a billion hours of flight. You can only prove that level of improbability through systematic, exhaustive engineering discipline.
Which means the mandatory adoption of the SAE ARP4754A V-Model. So our mission today is to explore the blueprint of this disciplined approach, the exact engineering steps that transition us from that high-level objective of fly 400 kilometers safely to the final certifiable system.
Okay, let's unpack this monumental framework. The V model is the foundation here. For those who see a V diagram and just think flowchart, Tell us, what is the V-model according to ARP4754A, and why is it so much more than just a suggested process?
Well, the V-model is the structure, the spine, that ensures no requirement is forgotten and no verification step is skipped. As a senior architect, I approach this using a top-down design and a MISI structure. Mutually exclusive, collectively exhaustive. Start at the top, defining the mission, and we systematically decompose that mission into traceable, implementable requirements. It's a mirror, because the left side of the V, the design side, must be perfectly matched by the right side, the verification side.
And the term you used earlier, traceability, that's where the V-model really earns its regulatory credit. Absolutely. Traceability is the cornerstone. Auditors don't want to see a product. They want to see the documentation proving how the product came to be. We have to achieve complete bidirectional traceability.
What does that look like in practice?
Imagine an auditor pointing to a single wire in the engine bay. We must be able to instantly show that that wire connects to a level 2 component requirement, which links up to a level 1 system requirement, which in turn links all the way back to a level 0 safety objective, that 1 in a billion goal.
So we're talking about managing tens of thousands of data points and their connections. Tools like Doors or Polarian aren't just useful, they're essentially mandated.
They are the central nervous system of the entire program. Without dedicated requirements management tools, managing those links, all the changes, the historical versions, it's humanly impossible.
And if something changes,
That's the beauty of it. The V-model ensures that if we change a single line of code in the motor control unit, the MCU, we can instantly see every high-level safety requirement that change impacts and ensure every single relevant test case is rerun. That auditability is what EASA and the FAA grant certification credit for.
Okay, so let's move to the left side of that V, the design side, starting at the top. This is the requirements decomposition. How do you use that MECE principle to ensure you don't miss any crucial element?
Well, we use MEC, mutually exclusive, collectively exhaustive, to ensure we cover the entire aircraft system without overlap or gaps. We start with the highest level, level 0.
All 0.
That's the overall vehicle performance and safety envelope. So things like maximum range, payload capacity, and that catastrophic failure rate we keep mentioning.
And from there.
Then level 1 is the system level. For our P-13 system, this means defining the required thrust for a vertical maneuver in hot and high conditions, the precise battery energy capacity needed for emergency reserves, and the exact energy balance for that whole intercity mission profile.
And finally, those level 1 requirements funnel down to level 2.
Level 2 is the component level. So here, we specify the detailed behavior of the vehicle control unit, the VCU processor like its required clock speed and determinism, or the torque characteristics of the P3 motor, or even the specific communication protocol standards for the battery management system. The goal of the left side is to convert those abstract mission goals into quantifiable, measurable technical specs.
You mentioned something absolutely critical earlier.
Yeah.
We don't design for performance first. We design for safety first. This is the safety precedence strategy dictated by SAE ARP4761. How early does the safety team get involved in shaping the architecture?
Day 1. From the very beginning. Safety is not a feature you add on, it is the fundamental architectural driver. We run the functional hazard assessment, the FHA, and the preliminary system safety assessment, the PSSA, before the engineers have even finalized where the major components are going to go. We're actively hunting for catastrophic single-point failures.
That sounds great in theory, but how does a paperwork exercise like an FHA actually impose massive physical architectural changes? Can you walk us through the concrete example of the 800-volt bus?
This is a perfect illustration of safety driving design. Our initial PSSA identified the high-voltage bus as the #1 risk, the absolute highest.
How so?
If we had a traditional single 800-volt DC bus running through the aircraft, a short circuit, maybe caused by a mechanical chafing of a wire bundle, would be a single-point failure.
Single point of failure that takes everything down.
Everything. It would instantly trip the main contactors, leading to a total, unrecoverable loss of thrust across all propulsors. This immediately puts your failure probability far, far above that 10 to the -9 threshold.
So a safety assessment forced a massive pivot. What was the engineering solution to eliminate that single catastrophic failure path?
The safety team mandated the adoption of a split-bus architecture. Instead of one main power line, the system is designed with 2 completely separated power distribution buses. They're linked only by controllable, certified cross-feed contactors.
I see the safety benefit, but as a host, looking at the complexity, I have to ask, doesn't adding a split bus mean twice the wiring, twice the control complexity, and twice the number of contactors and relays, doesn't that just double the number of things that can fail?
That is the essential, difficult trade-off, and that's why we call it managed redundancy. And you're right, it does add complexity, mass, and cost. However, a single point failure in the traditional architecture causes a catastrophic loss.
Whereas in the split bus,
In the split bus architecture, a failure on one bus is only a major failure. The system isolates the faulty bus in milliseconds and continues flying safely on the remaining bus. So we trade a high probability of total failure for a very low probability of partial failure. This decision alone is the difference between certifiable and non-certifiable in the enhanced category.
that is a phenomenal example of the V-model forcing safety into the very foundation of the design. Now let's flip to the right side of the V, the verification side. You mentioned the crucial distinction between verification and validation.
This distinction is non-trivial, and people often mix them up. Verification is objective and technical. Did we build the system to the specifications we wrote down?
So does it meet the spec sheet?
Exactly. For instance, we verified that the physical P3 propulsion motor, when we put it on a bench test, can indeed hit its nominal 110 kilowatt output. It's a box check against a level 2 requirement.
And validation moves beyond that component check.
Validation is subjective and mission critical. Did we build the right system for the overall safety objective? We have to validate that the 110 kilowatt output of the P3 motor is actually sufficient when combined with all the other systems to support continued safe flight and landing, CSFL.
And you test that in a failure scenario.
Right, like an engine failure on one engine inoperative, or OEI. The V-model forces us to look beyond just component performance and ensure the integrated system is fundamentally safe for the entire mission envelope. To execute the right side of that V-model, we rely on a staged approach, the verification pyramid. It is arguably the most disciplined and costly part of the entire program, but it's absolutely essential for managing risk.
What's the central mantra of this staged verification pyramid?
It's the shift-left strategy. In aerospace engineering, the later you find a bug, the more exponentially expensive it is to fix.
Right.
Finding a flaw in the high-level logic model level 1 of the pyramid might cost $5 and 5 minutes to fix. Finding that same logic flaw in the physical Iron Bird, which is level 4, might cost $2 million, destroy expensive hardware, and delay your type certification by 6 months.
That analogy of finding a typo in an email draft versus finding it in 10,000 printed books makes the economic case for shifting left immediately clear.
Exactly. Our target is to eliminate over 60% of all potential design flaws, logic errors, and control algorithm defects using low-cost virtual testing before we ever apply power to the actual expensive flight hardware.
So we start at the widest base of the pyramid, level 1, the virtual integration platforms. Tell us about model-in-the-loop, or MIL.
MIL is the birthplace of our logic. It lives entirely in the digital domain think MATLAB Simulink. We have 2 primary models running here. The plant model, which is the physics of the aircraft, its inertia, the thermodynamics of the ICE, the electrical response of the battery.
The virtual aircraft.
The virtual aircraft. And then you have the controller model. That's the algorithm that decides when to engage K0, how much torque P3 needs, and how to manage the energy management strategy, the EMS.
And the focus here is on the strategy.
Purely on validating the high-level strategy. Does the logic survive extreme rapid-fire Monte Carlo simulations across the entire flight envelope? Can the EMS decide whether to run the ICE at optimal fuel efficiency or use P1 to generate more battery charge for an upcoming landing? We answer those questions here.
Once that high-level strategy is mathematically proven, you move on to checking the language, the code with software in the loop, or SIL.
SIL is the sanity check on the actual software implementation. We take the embedded code, the CC++ or the automatically generated code that will actually run on the VCU, and we run it against the same plant model.
So you're checking the translation.
Exactly. This verifies that the translation from our beautiful mathematical model into executable code didn't introduce any unexpected errors, ensuring we meet strict software compliance requirements for systems that are DALA Design Assurance Level A.
Now, we take the crucial step up to level 2, controller hardware in the loop, CHIL. This is the first time the real flight hardware is introduced. What specific hardware are we talking about?
We integrate the actual flight control boards, the vehicle control unit, the VCU, the battery management system, BMS, and the motor control units, the MCUs. These are not simulators. They are the literal boards that will fly the aircraft. We plug them into a high-fidelity, real-time simulator like a D-Space Scalexio or an NI-PXI system.
So the physical VCU board is receiving simulated sensor data, making real-time decisions and sending out real high-speed control commands, even though the aircraft is still just a model on a computer.
Precisely. The simulator runs the physics model with microsecond precision, feeding the VCU resolver signals, RVDTs, those are rotary variable differential transformers, just fancy positional sensors, and CAN-FD communication messages. The verification focus here is not the logic, which we already checked in MIL, but the real-time performance on the target hardware.
And the timing requirement you mentioned earlier, the less than 10 millisecond VCU torque arbitration delay, that is absolutely critical here.
It is the CHIL red line. If the VCU takes 11 or 12 milliseconds to process sensor data and arbitrate the required torque between the ICE P1 and P3, the system is non-compliant.
Why? What happens at 11 milliseconds?
Because during critical mode transitions, that delay translates into instability, which violates the jerk limits we talked about and could lead to a loss of control. Deterministic rapid responsiveness is proven in CHIL. It has to be that fast.
If CHIL tests the brains, level 3, power hardware in the loop PHIL, must be where you test the muscle, the power stages.
Correct. We escalate complexity by integrating real power electronics. This means the actual silicon carbide or 6K inverters, the flight-rated power cabling, and even the motor itself.
But not the battery.
Not yet. We don't use real batteries or large mechanical loads yet. Instead, we use highly dynamic power emulation equipment, things like the AVL e-storage or Chroma Lemtino 20 battery simulators, which can source and sync massive amounts of power instantaneously.
What risks are you targeting at this level that were invisible back in CHIL?
We're looking for physical phenomena, electrical energy quality, high-frequency harmonics, and control loop stability in the power stages. CHE inverters switch incredibly fast. We need to verify that when a huge load spike occurs, say P3 is commanded to full thrust, the real inverter hardware can handle that electrical transient without blowing a gate driver, causing unexpected current ripples, or oscillating out of control.
You mentioned the incredibly strict real-time requirement for simulation fidelity. Less than or equal to a 50 microsecond step size for high-frequency models. As a generalist, that seems like a tiny number. Why is missing a microsecond so catastrophic for the system?
It relates directly to the physics of the SAE converters. These devices switch so fast that a high-frequency voltage transient, a spike, or a surge can occur in microseconds. If our simulation step size is, say, 100 microseconds, we are effectively blind to the peak of that transient event.
You just don't see it.
You don't see it. We might see the component survive a stable 800 volts, but we miss the 1500 volt spike that actually destroys the inverter's gate driver or prematurely ages the component. That fidelity is necessary to achieve a certifiable prediction of hardware robustness.
And for slower effects like thermal management, you can relax that, right?
Exactly. For slower effects, like the rate at which the motor heats up or the thermal mass of the cooling system, a step size of a millisecond or less is acceptable. But the core challenge of PHIL is running these vastly different time domains concurrently in real time.
Which brings us back to strategic component selection. Why are we seeing specific requirements for industry standard equipment like D-Space or certain battery simulators? Isn't that anti-competitive?
It's not about preference, it's about regulatory credit. When we submit data to EASA for a design assurance level A component, the regulatory authority requires proof that the test was conducted with hardware known for its reliability, its deterministic execution, and its documented capability for specific functions, particularly fault injection.
So it's about trust in the tools.
It's entirely about trust. If you use a consumer-grade system, the auditor will question the validity and repeatability of your 10 to the minus 9 proof. Using systems like D-Space Galexio ensures the infrastructure itself is certifiable.
And let's talk about the mandatory high-end data acquisition gear. The DAQ, like HBK, Genesis, or Duosoft Sirius. You specify 1000 VCAT3 isolation and a 1 megasample per second sampling rate. Why is this specific, expensive gear necessary?
2 reasons: safety and fidelity. First, we are measuring 800 volts. The 1000 VRT isolation is mandatory to protect the human operator and prevent the measurement equipment itself from becoming a failure point or transmitting high voltage transients back into the low voltage network.
Okay, that's the safety part. What about fidelity?
The 1 megasample per second sampling rate is about fidelity. Just like with the 50 microsecond simulation step, we need to capture those high-frequency transients. A single microsecond current ripple can indicate a flaw in our filtering or grounding strategy. If we sample slower, we smooth out those critical defects, and we might assume the system is stable when, in fact, it is not. This DAQ gear is non-negotiable for capturing definitive, certifiable data on high-frequency electrical faults.
We've ascended the pyramid, finding and fixing risks in the virtual and semi-physical realms. Now we reach the apex, the full-scale physical testing rigs, starting with the Copperbird.
The Copperbird is our dedicated high-voltage electrical laboratory. Its entire purpose is to integrate the actual high-voltage distribution network, the cabling, the power electronics, and all the associated safety systems, everything that deals with the 800-volt bus.
So it's the electrical system, but without the mechanical parts moving yet.
Exactly. It's the platform where we prove electrical integrity before we introduce complex, real-world mechanical coupling.
What are the primary objectives in the Copperbird?
We run extensive power quality checks, verifying that the voltage fluctuation stays within a very tight band, typically less than or equal to ±10% during major load shifts and transitions.
And if it doesn't?
If we have too much ripple, we degrade the battery and compromise the entire system. We also conduct our initial, critical, full system electromagnetic interference and compatibility EMC tests here. We're listening for the high-frequency electronic noise generated by those SINC inverters.
And this rig is the physical proof of concept for the safety architecture we designed earlier, the split bus.
Exactly. The Copperbird is the primary means of compliance, the MOVE, for proving our single-point failure immunity. We physically run current through the 800-volt network, and then, using specialized fault insertion equipment, we physically create a short circuit on one side of the split bus.
You actually shorted out on purpose.
We do. And we verify that the control system detects the fault, and that the cross-feed contactors successfully isolate the faulty bus segment in milliseconds, allowing the system to maintain power on the other half. This is the moment we physically demonstrate that the catastrophic failure path identified in the FHA is closed off, satisfying the SC VTOL requirements.
That is proof by torture. Now, the final step before the aircraft is assembled, the Ironbird. This is the full physical twin of the propulsion system, right?
The Ironbird is the ultimate integration test and the most expensive rig we build. It's a one-to-one scale environment, integrating every real mechanical and electrical component. The ICE, P1 ISG, the P3 propulsion motor, the K0 clutch, the flight-certified battery pack, and the actual thermal management system, the TMS.
Why is it necessary to build a one-to-one scale replica of the propulsion system, even mimicking the wiring harness layout? Can't we just test the components together on a bench?
We have to replicate the physical environment because high-frequency electrical behavior is utterly dependent on geometry. If the flight wiring harness is 5 meters long and runs next to a crucial avionics box, but your test bench harness is only 1 meter long and routed differently, your EMI results and your signal delays will be completely inaccurate.
So the layout itself is part of the test.
It has to be. The Ironbird must strictly adhere to the actual aircraft layout to verify real-world wiring harness impedance, signal delays, and authentic EMI coupling characteristics.
The single most complex element to verify must be the mode switching, that handover between pure electric and hybrid cruise, managed by the K0 decoupling clutch.
It is the moment of maximum risk and complexity. The control system has to synchronize the P3 motor speed, the ICE speed, and the battery state, and then engage K0 seamlessly. The specification mandates a rigorous durability test. The Ironbird must execute a minimum of 5,000 cycles of the vertical takeoff EV to cruise, parallel transition, and back again.
5,000 cycles? That's a massive commitment of time and resources.
It simulates the mechanical life of the clutch and the control stability over the aircraft's design service goal. I mean, the operators running the Ironbird often joke that they know the engine synchronization sequence better than the final test pilot will because they've executed it thousands of times under every conceivable fault scenario.
And that seamless transition has strict, hard metrics under FUNC VER01. Power interrupt must be less than 50 milliseconds, and the jerk must be less than 0.2 G.
These are passenger comfort and safety metrics. The less than 50 meters power interrupt ensures that the pilot doesn't feel a sudden, unexpected drop in thrust when the control system swaps power sources.
And the jerk?
The less than 0.2 G jerk limit, less than 1/5 of the gravitational force, is essential for avoiding passenger nausea or distress. If the transition is rougher than that, it's not certifiable for commercial passenger transport.
How do you achieve that smoothness, especially when you are coupling a combustion engine, which inherently produces vibrations and torque ripple, into a precision electric drivetrain?
That is the function of active damping, and it's a crucial verification point on the Ironbird. We use the P1 integrated starter generator, the ISG, as a dynamic electronic shock absorber. The ICE naturally produces torque ripple.
Right.
The P1 ISG has to sense that ripple and actively inject counter-torque pulses into the mechanical shaft. It's like noise-canceling headphones for vibration to dampen the disturbance. We must verify that this torque fill protects the mechanical shaft from fatigue and ensures the smooth output required for that 0.2 G jerk limit.
Finally, the Iron Bird has to stress test the thermal system under real load.
Absolutely. FUNC VER03 requires that we integrate the actual thermal management system, the TMS, the pumps, the radiators, the coolant lines. We run scenarios that generate maximum heat, like a prolonged high-load hover or a maximum climb rate in a high ambient temperature environment.
And what are you looking for?
The verification objective is to ensure that the TMS is effective enough to prevent any component, especially the battery cells, the P3 motor, or the CC inverters, from hitting their temperature limits. If they hit those limits, the system triggers protective thermal derating, which means an unexpected, uncommanded reduction in power output. That is a dangerous situation that renders the system not compliant.
We've established the architecture and the test platforms. Now let's get into the specifics of what success looks like, the measurable red lines for performance and fault tolerance. Starting with the core mission, energy management strategy, the EMS.
Right. FUNC VRZ2 focuses on the efficiency of the EMS. Because the P13 hybrid uses fuel and electricity simultaneously, the VCU runs these incredibly complex optimization algorithms, SOC balancing, P1 duty cycle adjustment, fuel flow control. We must verify on the Iron Bird that the actual fuel burn achieved across the entire mission profile is within 2% of the predicted mathematically optimized mission model.
That 2% margin sounds incredibly tight. What happens if the system is, say, 5% off?
If we exceed the 2% margin, it means the EMS algorithm is inefficient, and the aircraft will run out of fuel or battery reserves earlier than predicted. That compromises the required safety reserve margin. The entire EMS logic needs to be retuned, leading to massive delays. This is a crucial financial and safety benchmark.
And as we discussed in CHIL, thrust response is life or death during maneuvering.
Yes, the VCU must command, and the propulsion system must deliver. The requirement is absolute. Thrust must reach 90% of the target value from the initial command input in less than 50 milliseconds.
Faster than human reaction time.
Much faster. It's necessary for stable flight control, especially in turbulence, and for the rapid, precise execution of failure recovery maneuvers.
Now for the tests that prove that 10 to the -9 safety target. Rigorous failure mode verification. This is where we actively try to kill the system.
This is FUNC VER04, single point failure tolerance. We use highly specialized physical fault insertion units, FIUs, that are capable of simulating the most insidious physical failures: open circuit, short to ground, short to battery, and pin-to-pin shorts. We inject these faults into every single critical sensor line, actuator command, and control unit.
When a fault is injected, the system can't just throw an error code and quit. It has to keep flying.
Correct. The core of this test is verifying that the system executes a three-step process and does it rapidly. First, identification, detecting the fault. Second, isolation, disconnecting the faulty component. And third, reconfiguration, rerouting power, or redistributing thrust to the remaining functional propulsors.
And how fast does that have to happen?
For critical failures, the entire process from fault injection to stabilized reconfiguration and recovery thrust must occur in less than 100 milliseconds. That rapid reaction time is essential for the flight controller to maintain attitude and prevent the aircraft from entering an unrecoverable state.
Beyond physical wiring faults, the nervous system of this hybrid aircraft, the communications layer, must also be stress tested.
Absolutely. Since we rely on deterministic, high-integrity networks like Ariane 6604 or AFDX or T-Tethernet, we must confirm resilience. The test bench has to simulate protocol-level errors, packet loss, sudden latency spikes, or deliberate data corruption on the network.
So you're messing with the data itself.
We are. We verify that if a crucial thrust command packet is corrupted, the VCU redundancy logic instantly switches to the secondary, identical communication channel without any perceptible interruption in power delivery.
Let's look at the functional safety mechanisms defined by ARP4761, the internal software defenses. Test Save AV1 deals with catching bad data.
That's the cross-check verification of the command monitor, or common architecture. This is a critical safety principle. The control command channel is always running alongside an independent monitor channel. We simulate a scenario where a sensor doesn't fail catastrophically, but instead begins to slowly drift out of tolerance.
Which is a very sneaky kind of failure.
The most insidious. The risk here is that the primary controller might not recognize the drift as a failure, but the monitor channel running separate software must detect the growing discrepancy between the two readings. We verify that the monitor channel flags the error and cuts the control command within less than 20 milliseconds of that discrepancy exceeding the threshold. This prevents the aircraft from flying based on subtly corrupt data.
And if the software crashes entirely? The ultimate digital emergency.
That's Test Safe S02, the watchdog test. We intentionally induce a software deadlock or an infinite loop, a total VCU program hang. We must prove that the external hardware-based watchdog timer recognizes the cessation of the VCU's periodic signal and triggers a hard reset.
And that reset has to be controlled.
It must force the system into a predefined, safe operating state within the time boundary required to prevent the physical system from running away based on old, stalled commands.
Finally, returning to the highest risk area, the 800-volt system. Test Safe 03. HVIL verification.
The High Voltage Interlock Loop, or HVIL, is the safety barrier protecting ground crew and passengers from the massive stored energy in the battery. We perform this test on the Copper Bird. We simulate a catastrophic physical compromise. For example, a maintenance technician accidentally disconnecting an HVIL connector.
And the system has to react instantly.
Instantly. We verify that the high-voltage contactors open immediately in less than 10 milliseconds from the physical break to the contactor opening. Furthermore, the active discharge circuit must then bring the bus voltage down to a safe, touchable level, typically below 60 volts DC, in less than 5 seconds. These are absolute, non-negotiable human safety metrics that define system acceptance.
Proving functionality and resilience only covers one part of the certification matrix. The other half is proving the system can survive the harsh reality of the operational environment, which is governed by these massive standards like DO-178C for software and DO-160G for hardware.
And achieving compliance in these standards is where the vast majority of the program budget is spent. Let's start with the software gold standard. RTCA DO-178C, specifically for our flight-critical systems which fall under Design Assurance Level A, DALA.
What exactly does DLA demand from us?
It demands what is known as 100% Modified Condition Decision Coverage, or MCDC. This is an incredible level of rigor. Standard testing might verify that if A is true and B is true, the outcome is C.
Okay.
MCDC requires us to prove that every single condition within a complex decision structure independently influences the outcome.
Can you give an example?
Imagine a complex conditional statement in the VCU code that decides how to engage the K0 clutch based on speed, battery SOC, and altitude. If you have 5 conditions, MCDC requires test cases that prove that changing condition 1 alone flips the final outcome, regardless of the state of the other 4. It is exhaustive.
That sounds like an order of magnitude increase in effort. What does achieving 100% MCDC mean for the development timeline and budget compared to a non-safety critical aerospace program?
It's an enormous cost multiplier, often a 5 to 10 times increase in verification effort alone. You need highly specialized tools and an army of dedicated verification engineers writing tests, and then writing code to prove the tests cover every possible logical path. It adds months to the schedule, but it is the regulatory proof that the code is free of latent, unexpected logical flaws that could cause a catastrophe.
Now let's pivot to environmental resilience. RTCA DO-160G, the P13 system being a hybrid, presents some really unique physical challenges.
Starting with vibration, which is Section 8. The P1 motor and its controller are mounted right near the ICE. The combustion engine produces intense, random, high-frequency mechanical vibration. Any component in this zone has to pass curved W-level high-intensity random vibration tests.
You're shaking it to death, basically.
We spend countless hours shaking the hardware until we break it, just to prove the final design survives the worst-case engine environment. If a connector or a solder joint fails under the stress, you lose power mid-flight.
And the high-frequency switching noise from the Seeing inverters must make the EMC testing brutal.
EMC, Sections 21 and 22, are certification killers. CMME inverters switch at frequencies above 40 kHz, generating significant electromagnetic noise. We have to prove in an anechoic chamber that the radiated emissions from our 800-volt components do not interfere with the aircraft's fundamental systems, the navigation equipment, the radio altimeter, or the flight control data buses.
And it's not just what's radiated.
No, we also test for conducted emissions traveling back through the power lines. This noise control is incredibly difficult at these power levels.
There is also the challenge of power coupling between the high-voltage side and the sensitive low-voltage avionics.
That's power input, Section 16 verification. We have to test the resilience of the 28-volt avionics system. When the P3 motor suddenly draws massive current from the 800-volt bus during acceleration, the resulting magnetic fields and ground current transients must not cause momentary functional anomalies or brownouts in the sensitive 28-volt computers, which run the flight controls and cockpit displays.
Let's spend some significant time on the most unique challenge of the 800-volt eVTOL platform, one you call the hidden assassin in the specification: high-altitude physics and Paschen's law.
This is a silent killer in high-voltage aerospace. Paschen's law describes how the dielectric strength of a gas air, in this case, changes with the product of pressure and distance. As an aircraft climbs, the air pressure drops significantly.
Right.
And low air pressure, counterintuitively, dramatically reduces the insulating capability of the air between two high-voltage conductors.
Wait, I always thought thin air meant less material to conduct electricity. Why does low pressure make it easier to arc?
It's because the physics changes how electrons move. At sea level, air is dense, and electrons traveling between 2 points constantly collide with gas molecules, which slows them down. At a certain point of low pressure, say around 25,000 feet, depending on the temperature, the air molecules are sparse enough that electrons can accelerate across a gap without colliding, reaching ionizing velocities.
And that starts a chain reaction.
It triggers a runaway process called corona discharge or partial discharge, which can rapidly lead to a full arc flash, shorting the 800-volt bus. This is why high-voltage components have to be tested in a vacuum chamber that simulates those low-pressure, high-altitude conditions.
So you are looking for the point at which those microsparks begin, the partial discharge inception voltage, or PDIV.
Exactly. The verification requirement is strict. The PDIV must maintain a minimum 1.5x safety margin over the maximum operational voltage. If our system operates at 800 volts, we must prove that partial discharge does not begin until at least 1200 volts in the worst-case low-pressure atmosphere. If we fail this test, the entire high-voltage design is fundamentally unsafe for high-altitude operation. It is one of the most resource-intensive and often overlooked physical compliance gates.
Finally, battery safety, governed by DO 311A. Thermal runaway is the great fear, and the solution seems to be containment, not just prevention.
That's the key shift in regulatory philosophy. We have to accept that statistically, a single-cell failure will occur over the lifetime of the fleet. The requirement is to prove thermal runaway containment. Following a single-cell thermal event, we must demonstrate that the fire and hot gases are contained within the battery bay for a minimum of 15 minutes.
Why 15 minutes?
The 15-minute margin is the minimum period required for the flight crew to recognize the catastrophic failure, execute emergency procedures, and reach an acceptable safe landing area. Crucially, we also have to prove that during those 15 minutes, there is no propagation of fire or hot gases into the passenger cabin. That is the primary metric protecting life, and it's verified through aggressive, live destructive testing of the battery module structure. The final chapter of the engineering blueprint is the definition of the system acceptance criteria. This is where we distill the thousands of tests and checks into a few absolute quantifiable metrics that satisfy the type certification process. If these are not met, the program stops.
Let's start with integrity benchmarks. The 100% requirement pass rate sounds brutal in an environment this complex.
It is absolute. Every single system-level requirement derived from the V-model must be marked pass with objective evidence. Furthermore, all catastrophic and hazardous failure modes identified in the FHA and PSSA must have their mitigation strategies validated successfully via fault injection. There is zero tolerance for unmitigated critical risk.
Now for the performance KPIs we measured on the Ironbird. Let's re-summarize those agility targets.
Speed defines safety here. Mode switching time. The total time taken to transition from EV mode to parallel mode, including clutch engagement and torque fill, must be less than 200 milliseconds.
And the thrust response.
The thrust response delay from command to 90% target thrust must be less than 50 milliseconds. These targets ensure the VCU can react faster than any environmental disturbance or pilot input can destabilize the aircraft.
And the high voltage safety response times we confirmed in the Copperbird.
These are hard limits for human protection. The HVIL shutdown response time from the physical break to the high-voltage contactor opening must be less than 10 milliseconds. For post-failure resilience, after a critical component is physically disconnected, simulating a permanent actuator failure, the system must successfully detect the fault, reconfigure power, and stabilize thrust within less than 100 milliseconds.
We've talked a lot about controlling the electronics, But physical containment of kinetic energy is also a huge part of this, specifically the SCE-19 rotor burst containment requirement.
Absolutely. The P1 and P3 machines are spinning at incredibly high rotational speeds. If there is a catastrophic structural failure, the rotor may disintegrate, turning the motor into a fragmentation grenade.
Wow.
SCE-19 mandates that the motor casing must pass destructive testing, proving that the high-energy fragments will not breach adjacent critical structures.
Why is this such a high priority for this type of aircraft?
In an eVTOL, the motor nacelles are often located immediately adjacent to the high-voltage battery pack, which is highly flammable, or near vital fuel lines for the ICE. If a rotor fragment breaches a battery pack, you initiate thermal runaway. If it breaches a fuel line, you have a massive fire. So the certification requirement is literally about proving we can physically contain an explosion using sophisticated casing design.
So the complexity isn't just managing the digital flow of information. It's about managing the kinetic energy of failure.
It's the definition of mechatronics integration at the highest level of safety. Finally, the acceptance criteria hinges on the deliverable. We must submit a complete, traceable verification and validation document package, the VVPVVR, and the final System Safety Assessment, the SSA report.
And regulatory oversight here is absolute.
It's mandatory. EASA and FAA representatives must witness the testing for all critical safety items. The data must be impeccable, traceable back to the component level, and complete. That documentation package is the type certificate.
This deep dive into the P13 hybrid system has been a masterclass in risk management. It shows that building a long-range, safe eVTOL is not a matter of a single genius invention, but a methodical, disciplined, structural execution of risk mitigation.
I view this blueprint as the strategic pathway to commercial viability. The complexity of the P13 hybrid is immense, but it is manageable only through the rigorous, systematic execution of this tiered virtual to physical verification strategy. This structured approach is what converts perceived design risk into certifiable, measurable confidence for the regulators.
If the listener takes one actionable insight from this entire blueprint, what is the critical engineering investment they need to prioritize right now?
Without question, the immediate prioritized investment must be in the 1-to-1 scale Ironbird test bench. The HIL environment is superb, it gets you 90% of the way there, but you cannot perfectly simulate the real, chaotic, thermomechanical coupling under high load, the vibration of the ICE, the heat exchange of the TMS, the non-linear forces on the K0 clutch.
You can't simulate the physics perfectly.
You can't. The Ironbird is the only physical basis for certification credit that EASA and the FAA will accept implicitly for the final type certificate. You must test the physical twin.
The physical twin is the key to regulatory trust, which is a powerful business takeaway.
And if you are looking toward the future, the biggest, often overlooked safety hurdle in this entire industry is the battle against high-voltage physics at altitude. The implications of Paschen's law and the constant need to test and verify the partial discharge inception voltage are massive.
So the challenge isn't just about insulating an 800-volt system. It's about constantly fighting the atmosphere itself, which conspires to make the insulation fail as you climb. That silent physics-based threat, the hidden assassin, is a truly fascinating concept for our audience to mull over.
It defines the cutting edge of high-voltage aerospace safety engineering.
Thank you for guiding us through this incredibly detailed and rigorous engineering specification.
My pleasure.
And thank you, the listener, for diving deep with us into the blueprint for the future of flight. We'll catch you next time on The Deep Dive.